Good morning, one and all. So, today we will continue with the entropy that we have discussed in the last class. Now, I told you entropy means it is a measure of uncertainty or the average information per symbol. So, whose formula is depends only on the probabilities. Now, these are two formulas we use to calculate the entropy. Okay, you must remember these formulas. Now, so let me take one more concept called binary entropy function. So here what I do is, so I'll take a Bernoulli process. You know already Bernoulli process means there are only two possibilities. If you take x as a Bernoulli random variable, it can be either 0 or 1. Yeah, so x is a random variable of Bernoulli which takes on only two values. Now with the probability that x equal to 1 is p, probability that x equal to 0 is obviously 1 minus p. Now if it is so, can you write down the formula of entropy for this? So we have only two functions, two symbols. So how to write the entropy formula? So here, use this formula. Here I varies from 0 to 1. P naught, minus of common P naught log 2 P naught plus so on. So if you do so, now the entropy function for the Bernoulli random variable would be h of x that equal to minus p log p base 2 minus 1 minus p log 2 1 minus p. So this probability into log of this probability, next this probability into log of this probability. Okay. Now as I told you in the last class, entropy will be maximum when all the given symbols are equiprobable. Now since in the case of this Bernoulli trial we had only two symbols, so the probability of which symbol is equal, which means the probability of each and every symbol is 1 by 2. Now suppose that is one case. Suppose p equal to 0. If p equal to 0, what do you mean by that? So the probability that x equal to 1 is 0 at the same time, so this would be 1, which means the probability that x equal to 0 equal to 1. Okay. Now if p equal to 1, so this will be 1, this will be 0. Okay. So here something like this. We had only two symbols. So x takes on only two symbols, either 0 or 1. Correct? Suppose if p equal to 0, okay, if p equal to 0 means, so probability of x equal to 0 is 1, means this will occur for sure. Okay. If reverse happens, if p equal to 1 means what? Sorry, here I have taken reverse. This is sure. Okay. So if p equal to 1, what will happen? What do you mean by that? Which symbol occurs for sure? P equal to 1 means this is 1. So symbol 1 occurs for sure. Okay, anyway. Now, so I have drawn the graph between h of x versus probability. Okay. So h of x is nothing but entropy function. Now when p equal to 0, what about h of x? So p equal to 0 means this is 0. P equal to 0 means log 1. So this is 0. H of x is 0. When p equal to 1, p log 1, this is 0. P equal to 1 means this is also 0. Okay. So when p equal to 1 and p equal to 0, h of x is 0. So when it is maximum, when p equal to 1 by 2, what happens? When p equal to 1 by 2, what is the answer? So 1 by 2 log 1 by 2. So can you tell me what is the answer? The answer is 1. You try to solve it. Here, so when p equal to 0 and p equal to 1, h of x is 0. When p equal to 0.5, okay, of, now entropy would be maximum. How much is that? 1. So here it should be point, not comma. Okay. Now this is a binary entropy function. So here this is something like this curve. Okay. Now when it is maximum, when the entropy is maximum, when the symbols are equiprobable, which means, so the probability of symbol 1 is same as symbol 0, that equal to 1 by 2. How much is the maximum entropy? 1. Why it is 1? I told you. So the maximum entropy is log of, how much is that? Log of k base 2. That is upper bound on the entropy. So minimum entropy is 0. Maximum entropy is log of k base 2. What is k? The number of symbols. Here how many are there? 2. So which means log 2 base 2. How much is that? 1. Okay. So it follows the boundaries on the entropy. Okay. So you must remember this. So here it is 0 at both cases. At p equal to 1 by 2 it is maximum, that is 1. Okay. Because at p equal to 1 by 2 there is more uncertainty, that's why there is more entropy. Okay, right. Now let me take one more simple topic, entropy of English. You take English alphabets, so A to Z. If all are occurring with same probability, then what the entropy would be? Entropy per letter would be log of 26 base 2. Okay. Because so if all are equiprobable, what the probability of occurrence of each and every symbol would be? 1 by 26. Because we have 26 letters in the English literature. So this is would be 4.70. That is the uncertainty that will be maximum. Okay. But so generally that is not the case. Why? Because so however all the letters do not appear with the same probability. So generally these letters are more frequent and these letters are less frequent. If you take any English sentence, all the alphabet don't occur with same probability. So this is general observation is these letters occur frequently and these letters occurs very less frequently. Okay. Now anyway, so that is about simple entropy of the English. The maximum would be 4.70. Okay. So these symbols occurs frequently, or these letters occurs frequently, these letters occurs very less frequently. Okay. Now, so let us move on to discrete memoryless channel. Okay. Now here, so that is not that much important, but I will try to explain briefly. Okay. Now here I have a channel. Input is X, capital X. Output is capital Y. Okay. But so the capital X takes on capital J values. How many? Capital J symbols. What are they? X0, X1, so on, so on, X, capital J minus 1. So the input alphabet capital X has these elements. What are they? X0, X1, so on, so on, X, J minus 1. How many symbols are there at the input side? Capital J. In the same way, so the output symbol is capital Y. Output alphabet is capital Y. We call it as a input alphabet. This is output alphabet. Now the capital Y takes on how many values? Capital K values. What are they? Y0, Y1, so on, so on, Yk minus 1. So the capital X takes on capital J values. These are those elements. Capital Y takes on capital K values. These are these values. So X0, X1, Xj minus 1, Y0, Y1, Yk minus 1. Now this is the conditional probability. So probability that Yk is received given Xj is transmitted. Now here, so here this is small k, this is small j. What is small j? Where is from? From where to where? 0 to capital J minus 1. What about small k? Where is from? From where to where? 0 to capital K minus 1. 0 to capital K minus 1. Okay. It's just simple notation. You don't get confused by this. Okay. Now, so in the last classes we have discussed entropy. What is entropy formula? So that is very, very important. So I am repeating so many times because it is very, very important. You must know this formula. Now this is the formula of entropy. Correct? This formula or this formula. Okay. Now, so it is entropy of a symbol S. Correct? Now, so here we will find out another two types of entropies, namely joint entropy and the conditional entropy. Now h of x comma y is nothing but the joint entropy of x and y. What is x? What is y? X is the input alphabet, y is the output alphabet. Now, what the formula would be? Here, this is joint entropy, that's why there is a joint probability. Xj, Yk. P of Xj, Yk, here 1 by P of Xj, Yk. So, the formula is very much same. The only thing is, here it is for two random variables, x comma y. Okay. So, that's why two summations. It is joint entropy, that's why joint probability. What summation? Summation j equal to 0 to capital J minus 1. What are they? I told you already. So, j equal to 0 to capital J minus 1. Small j equal to 0 to capital J minus 1. That is for capital X. For capital Y, small k equal to 0 to capital K minus 1. It's just a little bit confusing is there, but you don't get that much confusion because it's just a notation. You can use any other notations also, no problem. Okay. So, this is for symbols in the input alphabet capital X. It is for symbols in the output alphabet capital Y. These are the joint probabilities. The formula is still same. Okay. So, that is the joint entropy. Now, in the same way, we have conditional entropy. What do you write here? We write, I think it is a mistake. So, this is the conditional probability. So, h of x given y equal to, okay. Now, so you must know these two types of entropies also. So, they are not much important, but you should have an idea at least. Okay. Now comes the another type of information that is called the mutual information. So, in the last class, we have studied self-information. I told you I of Si or simple information. Correct? Now, we will study the mutual information between x and y. So, it is x semicolon y, which means, so the common information between x and y, it is simply a common information that is shared between x and y. Okay. Now, so otherwise you can also define it as, so it means how much random variable x knows about random variable y or vice versa. How much x tells about y or how much y tells about x, which means how much one random variable tells about another random variable. Okay. So, how much x tells about y or how much y tells about x. Okay. Otherwise, how much information do they share in common? Simply, it is having an intersection of the two matrices, two arrays. Okay. Suppose you take A and B, you assume that is input, is output, something like that. Now, how much common element do they contain? How many do they contain? 2. Okay. So, the mutual information between A and B is, we can say 3 and 9. As simple as that. Okay. Now, so here I am not deriving any formulas for mutual information, but it simply depends upon h of x minus h of x given y. Okay. So, what is h of x? It is the entropy of the x. Here this is a conditional entropy. Entropy minus conditional entropy. Okay. Now, so this is the proper definition of the mutual information. What is that? It is a measure of uncertainty about the channel input which is resolved by observing the channel output. So, you try to understand this very logically. What I want to say is, now you know already, this entropy is nothing but indication of uncertainty. Okay. Otherwise, it is a measure of uncertainty. Here, what I want to say is, how much uncertainty is cleared or resolved by observing the channel output. Okay. You take a simple example. Okay. Simple logic. You take a channel, input is capital X, output is capital Y. Okay. here. So you don't know what is input is, you don't know what is x is, okay. But so you might have some assumption about x, you may think that it is 1 or it is 0, okay. But so by observing y, you may resolve some of your assumptions, okay. So by observing x, you may resolve some amount of uncertainty that you might have about capital X, okay. So that is called the mutual information, okay. So that is defined by like this. Is it okay? Now, so it is also defined as h of y minus h of y by x, either this formula or this formula. It also defined as, okay, sorry. Now, so I use this formula or this formula to find out the mutual information between capital X and capital Y. So it is simply indicates the common information that is shared between these two alphabets. They are capital X and capital Y. Okay. So these are some of the properties of mutual information. So they are symmetric, which means x semicolon y is same as y semicolon x. So that is very much clear from this formula. Okay. So mutual information is always non-negative. I told you while discussing the properties of information itself. So any information is always non-negative. Okay. It's always positive, which means it's always greater than or equal to 0. Yeah. So this is one more formula for the entropy. So sorry, for the mutual information. What is that? H of x plus h of y minus of h of x comma y. What is this? This is called joint entropy. What is x given h of x given y is what? Conditional entropies. These two are conditional entropies. This is the joint entropy. Okay, so these are three formulas you can use. This formula or these two formulas. Total, you can use any of these three formulas to find out the mutual information. Mutual means the information that is common between x and y. As simple as that. Okay. So one more thing I forgot to mention. So if x and y are independent, obviously there is no mutual information. I might have written somewhere, just try to here written. So they are independent. If they are independent, they don't share any common information. Okay. Then the mutual information is 0. Now here, so this is a very interesting one. So entropy is a self-information. Okay. So what is I of x semicolon x? Information about x that is given by x. Simply entropy. Okay. So I of x semicolon x equal to h of x minus h of x given x. So it is 0 actually. Okay. Now we are left with only h of x. Now here, so this is the Venn diagram which depicts the three formulas of the mutual information. Okay. So we had three formulas to find out the mutual information. These two and the last one is this one. Okay. Now this is a Venn diagram. Now this circle on the left hand side, this complete circle is h of x, and another complete circle to the right hand side is h of y. Now what is this portion? Only this portion. H of x given y. Okay. In the same way, what is this portion? H of y given x. Correct? Now, so what is the formula of I of x semicolon y? H of x minus h of x given y, which means h of x means this complete circle minus this part. H of x given y. Then you left with this part. only this part. Okay, that is one way of writing. Okay, next another formula is h of y minus h of y given x. What is h of y? This complete circle. What is h of y given x? Only this part. Now this part would be mutual information. So that is another formula. So what the last formula we had? H of x plus h of y minus h of x comma y. What is h of x comma y? This one. This is h of x comma y. Okay. So remember that. Then what is h of x? This part plus h of y means this part minus h of x comma y is nothing but this part. So you might have seen these kind of things already. Okay, it is something like finding the intersection, finding the union only. Okay. So I think I don't need to elaborate on this. Now this is a Venn diagram depicting all three formulas of the mutual information I of x semicolon y. Okay. So the intersection is the intersection of information in the x with information in the y. So this is the common or mutual information between x and y. As simple as that. Okay. Now, so here, so that is about the mutual information, entropy, information, and the entropy function, all those things. Okay, right. So now let us briefly discuss another topic. So that is called source coding theorem. Okay, source coding theorem. So this is very much important. Okay. Now what it says here is, you might have seen already. So there is something called source encoding. Okay. It is simple encoding only, but with some specific cases. Okay. Now, so here let me take a simple example. So one of the oldest source encoding techniques is in telegraphy. It is called Morse code. What is called? Morse code. It is one of the oldest source coding or source encoding techniques. It is called Morse code. Here what will happen? What do you mean encoding? Generally any source gives a symbol. Let me take a source is giving a symbol SI. Okay. Now for that we need to generate some other form. Maybe for SI we are generating 0 0, or you may generate 1 1, or you may generate 1 0 1. So for each and every symbol we are generating a corresponding binary sequence. So that is accomplished by source encoding. Anyway, so let me go to the Morse code. So it is one of the oldest source encoding. Now in this, what is happening here is, so the English alphabet capital E, okay, which is denoted by a dot, whereas the letter Q is denoted by this symbol. What symbol? Now, so what was happening here is, suppose you want to transmit some letters. Let us take, you have some sentence. Okay, EQ, you want to transmit E and Q. For alphabet E, what do you transmit? A dot. That is encoding. For alphabet Q, what do you transmit? I have taken up an example only. So for each and every alphabet there is a corresponding code word. But I have taken E and Q. Okay. For E, simply dot. For Q, this is a symbol that is used to encode. Okay. Now, so why I am taking E and Q? So there is a simple thing, that is, generally you take any English sentence, E occurs more frequently. Among all alphabets, generally E occurs more frequently. Okay. At the same time, Q occurs very less frequently, or it occurs very rarely. It is very rarely used. E is mostly used. It is a mostly used English alphabet in any sentence. This is very rarely used English alphabet in any sentence. That's why I have taken these two letters for the encoding purpose. But for each and every letter there is a corresponding code word. Okay. So for E we are using a shortest code word. What is the code word for E? Simply dot. For E we are using dash, dot, again dash. So a symbol or a alphabet which occurs very rarely is given a longest code word. Okay. At the same time, a letter which occurs very frequently is given a smallest length code word. Okay. Here, so one thing we need to understand here is a letter which occurs very frequently is given a small code word, whereas a letter which occurs very rarely is given a longest code word. But so one thing should be very clear that so this encoding should be unique, because suppose you are encoding like this, we should be able to decode also. For that purpose, this should be uniquely decodable. You must make sure that all these things should be uniquely decodable. Okay. Now, so this is simply encoding that was used in the olden days. Anyway, so I want to mention these things. Now it is considered as a variable length code. Why? Because we assign short code words to the frequent source symbol and long code words to the rare source symbol. It's called variable length code. Why? Because each and every symbol do not have same length of the code word. You can observe very clearly. For E, only dot is there. For Q, we have a dash, dot, dash. Okay. So the length of the code words are not same. Okay. So it's called variable length codes. Different symbols will get different length codes. Okay. We'll study elaborately about this, but it is a type of variable length source encoding. So generally, you might have studied like this. Suppose you have 4 symbols. Okay. So how to generate 4 code words? We use 2 bits in each symbol. What are they? 0, 0, 0, 1, 1, 0, 1, 1. Okay. You want 4 code words. You can generate them by using 2 bits. Suppose if you want 8 code words, what do? You use 3 bits in each symbol or in each code word. 0, 0, 0, 0, 0, 0, 1, so on, so on, so on, so on, 1, 1, 1. Okay. Now here, each and every symbol has got only 2 bits here. Here, each and every symbol has got 3 bits. They are called fixed length coding. The length is fixed. Each and every symbol has got only 2 bits. Here, each and every symbol has got only 3 bits. They are simply called fixed length. But here, it is variable length. Okay, the length will not be same always. It varies depending upon their probability of occurrence. Okay, I will take an example later. But okay, so the source encoding should satisfy these 2 things. So now it should be in binary form and it should be uniquely decodable. It is also very important. Okay, so these 2 are the requirement of a source encoder. Now, so this is the source encoding. Okay, generally what happens here is we have a source which emits a symbols at regular intervals of time. A symbol will be emitted. You take a English sentence, you may get a letter A. Maybe after some time you may get a letter C. You may get letter E. You may get letter Q. English alphabets. Okay. Now the source encoder should assign a binary code word for this letter A. Next for C, for E, for Q. So the job of this encoder is to assign a code word for each and every symbols. Okay. Now here, so SK is the kth symbol that is produced by the source, and the source encoder will convert this symbol into the binary sequence, that means sequence of 1s and 0s denoted by BK. What is BK? It is a code word for symbol SK, and the length of the code word is LK. The length of the code word is LK. Suppose Now the symbol is SK. So the code word is BK, that equal to 001. Now what is the length of this code word? 3. The length is 3 because it requires 3 bits. Okay, LK is 3. Okay, something like that. So let me take a simple thing. Now the source is emitting K symbols S0, S1, so on, Sk minus 1. Corresponding probabilities P0, P1, Pk minus 1. Corresponding code words B0, B1, Bk minus 1. Means for S0 the code word is B0, for S1 the code word is B1, so on, and the corresponding code word lengths. For length of B0 is L0, length of B1 is L1, so on. This is the scenario. I hope you are okay with the scenario. Now I want to calculate average code word length of the source encoder. What I do? See, remember, whenever I say average, you have to multiply with probability. P0 into L0 plus P1 into L1 plus Pk into Lk minus 1. I told you already. What is entropy? That is average information per source symbol. There also what you have done? We have multiplied probability into information. We have taken a summation. Okay. So whenever I say average means you have to multiply the probability into that particular term. Here I am saying average code word length, which means you have to multiply the probability into code word length plus take a summation. Now this is what the Pa into Li. Summation over I equal to 0 to capital K minus 1, Pa into Li. So the average, now what is the average code word length represents? Number of bits per symbol. It represents number of bits per symbol, which means how many bits you are transmitting for each symbol. Okay. So L minimum is the minimum value of L bar. So please make a notation of this. This is a simple notation. So L minimum is minimum possible value of L bar. Okay. Now, so please make a note of this. The coding efficiency is given as eta, that equal to the L minimum by L bar. What is L minimum? The minimum possible value of L bar. Okay. Obviously, this will be equal to less than equal to 1. Okay, I hope you are okay with this, because it is some kind of efficiency which is always less than equal to 1. Okay, so how it is defined? It is defined as L minimum by L bar. It is defined as L minimum by L bar. So what is L bar? It is the average code word length. What is L minimum? That is the minimum value of L bar. So it is efficient when the efficiency is 1. Obviously, we say that the code is efficient whenever it has got maximum efficiency that equal to 1 or 100%. That is quite obvious, right? Now comes the source coding theorem. What theorem says? Okay, I am not explaining in detail, but I am just giving you the statement of the theorem. Okay, how to determine this L minimum? It is given by the source coding theorem. How it is defined is, so the average code word length for any source coding is bounded as L bar is greater than equal to H of S. L bar is always greater than equal to H of S. That is a source coding theorem. This is the only theorem, just this term is enough. Now from this source coding theorem, what is the minimum value of L bar? H of S. Correct. Because if I say x is greater than equal to 2, obviously the minimum value of x is 2. In the same way, if I say L bar is greater than equal to H of S, obviously the minimum value of L bar is how much? H of S. L minimum is now H of S. Now H of S by L bar. Now this is the efficiency. Okay. Now, so this is a source coding theorem that is given by Shannon, a scientist Shannon. It is called Shannon's first theorem. What is the definition of source coding theorem? So the average code word length always will be more than or equal to the entropy of the particular discrete memoryless source. That is simple definition of the source coding theorem. Okay, you must add that statement. That's it. Okay. Right. So we stop here. Now this is about the coding efficiency of the source encoder. Okay.